I am Lucia Wu, and I'm a grad student at Yale School of Forestry and Environmental Studies. And here I study air pollution from wildfires, and I'm very excited to be here to be sharing my research, which suggests that wildfire smoke exposure in Alaska vary across space and time and is expected to increase in the future. Let me quickly go into presenter mode. Just a quick overview of my talk. I'm going to be discussing the link between wildfire smoke and human health, and the present-day wildfire pollution levels in Alaska, as well as the future mid-century levels. And I'm going to wrap it up by sharing lessons learned. Wildfire smoke impairs human health. When wildfires burn, they may generate large volumes of smoke, which primarily consists of particulate matter size 2.5 microns or smaller in diameter, or otherwise known as PM 2.5. The size of PM 2.5 is about 1/30th of an average human hair strand width. And to the graphic on the right, we can appreciate the size comparison where the pink dots denote the size of PM 2.5 and the gray tube represents the size of an average human hair strand. Because these particles are so minuscule, they can penetrate deep into our lungs and put us at an increased risk for respiratory or cardiovascular diseases. But what's really interesting about PM 2.5 from wildfires is that they may be more harmful than PM 2.5 from other sources. According to Giacomo Liu and al. 2016 study, they found that per 29.6 microgram per cubic meter increase of wildfire-specific PM 2.5, they observed 7.2% increase in respiratory-related hospitalization rate, or here referred as respiratory admission rate. But on the other hand, according to the Bell and al. 2008 study, they found that per the same concentration of PM 2.5 from all sources, they only observed about 2.81% increase in respiratory admission rate. I chose to study Alaska because, to the best of my knowledge, my study is the first to examine Alaskan communities exclusively for potential human health impacts from wildfire smoke exposure. And as we all know, Alaska may be experiencing more wildfire smoke exposure. If we look on the x-axis, we see the recent decades, and on the y-axis, the burn area in the units of 1,000 hectares per year. And the black bars denote the burned areas from all forest fires, while the gray bars represent human-caused fires. So the difference between those two bars represents the burned area from wildfires alone. And we see that that difference has been increasing since the 1980s. Additionally, the Alaskan population may be getting more susceptible. On the x-axis again are the recent decades going up to 2045, and on the y-axis is the population count in the units of thousands. And in each scenario considered by the Alaska Department of Labor and Workforce Development, we see that the elderly population who are 65 years or older with compromised immune system is expected to grow into the future. So the driving research question here is, how do wildfire patterns affect the human health of Alaskan communities? To address this, I conducted a non-occupational, meaning no firefighter exposure assessment of only wildfire-induced PM 2.5 in Alaska during the present day, as well as identify who are the vulnerable subpopulations in the present as well as the future, and also estimate what the wildfire PM 2.5 levels are going to look like in the future around the mid-century, including the associated health impacts. On the right, we'll see a map of all EPA PM 2.5 monitors that operated sometime between 1999 through 2014, and we see that the data from these monitors are not suitable to conduct such exposure assessment in Alaska because, number one, they measure PM 2.5 from all sources, not just wildfire smoke. Second, they provide information only on urban areas as opposed to all of Alaska. So what do the present-day wildfire-specific pollution levels look like in Alaska? And here I define the present day as 1997 through 2010. In estimating the present-day levels, I was fortunate to have access to a gridded model data set, which was a result from collaborations among Yale and Harvard atmospheric scientists. The fire data input was the North America Fire Emissions Database, which is based on the interagency fire report and utilizes the transport and deposition model called GeoCam models in order to estimate where the wildfire smoke may have traveled to. The graded data covers almost the entire state of Alaska, with the exception of a portion of Aleutians West, which contains less than 0.2% of the total Alaskan population. The grid cell size is 4 degrees by 5 degrees. And if you like to think in terms of miles and kilometers just like me, then please refer to the graphic on the right. And what I did was from the graded data set, I averaged the census tract level, the average exposure level for each census tract in Alaska using area-weighted average methodology. The data, again, it covers from 1997 through 2010, and I averaged the data across the years by month. For population data, I used the 2000 decennial census data. And my results show that the wildfire PM2.5 exposure levels during 1997 through 2010 are the highest in the interior Alaska, and for the month of July and August. We can see that the monthly average wildfire PM2.5 concentration can be as high as 30 to 35 micrograms per cubic meter, as denoted by the color red here in this map. At this point, I'd like to communicate how high or dangerous this monthly average level of 30 to 35 micrograms per cubic meter of PM2.5 could be. Depicted here is the time series of 24-hour average PM2.5 from all sources level during the summer of 2004 in downtown Fairbanks. We see many days that exceeded the EPA 24-hour average standard of 35 micrograms per cubic meter, which is denoted by the red line towards the bottom of the graph. In fact, a number of these days even exceeded into the moon-colored region, which is classified as the hazardous air quality. And hazardous air quality pose almost immediate health repercussions for everyone. Next,
excuse me, hello?
Hello, yes?
Hello, this is Rangshai calling from FAA. In this figure, like if you were to go and, let's say, quote a number for a urban area in here in the Northeast, for example, New York or Washington, what would that number be like?
I'm sorry, could you repeat that question one more time?
So I'm looking at this episodes where this to get a feeling for the y-axis, what would the numbers look like for an urban area like Washington or New York City?
Sure. All of the cities in the U.S. need to have need to be below the 24-hour average standard of 35 micrograms per cubic meter. So, for example, the city of Los Angeles, for example, is out of compliance and experience greater than 35 micrograms per cubic meter. But cities in the Northeast, for example, I believe most of them are below the 35 micrograms per cubic meter for the 24-hour average. And apologies, I forgot to mention that the monthly average for June and July during the summer of 2004 in Fairbanks was about 30 to 35 micrograms per cubic meter. So this is an example of what the monthly average of 30 to 35 micrograms per cubic meter of PM2.5 could be. Does that answer your question?
So most of the cities are compliant, which means that they're below the red line.
Yes, yes.
Yeah. Okay, thank you.
And this is just one snapshot. This does not in any way represent what the residents in the city of Fairbanks experience on a daily basis. This, as my audience is well aware, the summer of 2004 was very special. I'll be happy to take additional questions as I go on, so feel free to ask them. Next, I determined which subpopulations have the highest and the lowest wildfire PM2.5 exposure levels for the following population characteristics listed here. And I found that for developed settlement type, race, ethnicity, native tribe, and occupation industry, These population characteristics demonstrated the biggest difference in wildfire PM2.5 exposure level among subpopulations, and I'll be discussing them in my presentation. What I mean by developed settlement type is, well, which area is urban, rural, or remote rural? And I define here remote rural as those areas that have very limited access to road or ferry. And as you can see, most of Alaska is indeed remote rural. From my analysis, I found that urban area residents experience higher wildfire PM2.5 exposure than those who reside in rural and remote rural areas. In this graph, on the x-axis are the summer months, on the y-axis is the monthly wildfire PM2.5 level in the units of micrograms per cubic meter. And we see that the maroon colored line represents the exposure level for urban area residents, and that it's higher than those of rural and remote rural areas residents' exposure level. And if we look at the table, it's a different way to visualize the information. The summer average exposure level for urban area residents is about twice as high as those for rural and remote rural area residents. And we see that significantly more people do reside in these urban areas. We have seen these maps before. The left map shows which areas of Alaska are urban, rural, and remote rural, and on the right hand is a map that shows the distribution of wildfire PM2.5 levels across Alaska. And we see that a higher proportion of rural and remote rural areas are located where exposure levels are low. For race and ethnicity, my results suggest that African Americans experience the highest exposure level, and American Indians or Alaskan Natives experience the lowest level. In the graph, the sky blue line represents the exposure level for African Americans, while the green line represents the exposure level for American Indians or Alaskan Natives. And if we look at the table, we see that the exposure level for African Americans is about twice as high as that for American Indian or Alaskan Natives. Upon examining the population density maps, we see that these groups' exposure levels are driven by their residential spatial patterns. We can see that the African Americans are concentrated in the interior Alaska, namely Fairbanks, and American Indian and Alaskan Natives are concentrated along the western coast where the exposure levels are low. And again, the exposure level in the interior Alaska is high. But even within this lowest exposure group of American Indian and Alaskan Natives, the exposure levels varies by native tribes. For example, Alaska Athabascans experience by far the highest exposure level. Again, it's denoted by the sky blue line. And the other Alaska Native category group experience the lowest, and their exposure level is denoted by the green towards the bottom. And if we look at the table, we do see that the Alaska Athabascans experience about 6 times as high of exposure level as that for other Alaskan Natives. And we also see that the Alaska Athabascan is the second biggest subpopulation by native tribes. Again, with the population density maps, we see that the Alaska Athabascans are concentrated mainly in the interior where the exposure levels are high, and the other Alaskan Natives are concentrated along the southern tip of Alaska where the exposure level is low. Furthermore, the wildfire PM2.5 exposure varies by occupation industry. We see that the construction workers experience about 1.5 times as high as that for manufacturing workers. And in the graph, the construction workers' exposure level is denoted by the red line, and the manufacturing workers' exposure level by the purple line. Compared to the population characteristics that we examined previously, the difference in wildfire PM2.5 exposure level here is more subtle. Next, I estimated what the future wildfire PM2.5 levels would look like under climate change. And here I define future as 2047 through 2051. The data and the methodology remain very similar to those that were used in the present day analysis. In estimating the future levels, I had, again, great luck in having access to another gridded data model set from the same collaboration group that utilized the ensemble of 13 climate models and geochem-based transfer model, and the data has been simulated under the IPCC's A1B climate change scenario. And the A1B climate change scenario is the middle-of-the-road growth scenario. But this time, I derived the gridded data set to the borough and census area, which is the county equivalent in Alaska. And the present day is defined as 1997 to 2001, and the future from 2047 to 2051. And my results show that almost the entire Alaska will be exposed to at least 100% increased wildfire PM2.5 levels under climate change by 2047 through 2051 relative to 1997 through 2001. I cannot emphasize how high those levels are. In fact, in certain parts of Alaska, they may experience up to 250 to 300% increased levels. So what is the change in wildfire PM2.5 under climate change? How does that translate to potential human health impact? Utilizing the concentration health function from Lu and L 2016 study, which is specific to wildfire PM2.5, I determined that the respiratory hospitalization rate from wildfire smoke in the interior Alaska for the elderly population will increase by 2 to 7% under climate change from the beginning of the century to about the mid-century. And we can see that the potential human health burden from wildfire smoke exposure is the greatest for the interior Alaska communities. To wrap up, I'd like to share some of my lessons learned. First, Alaska currently is experiencing high levels of wildfire-specific PM2.5 during July and August, especially in the interior. Second, under climate change, Alaska will experience increased levels of wildfire exposure, as well as associated health burden, mainly respiratory-related illnesses. And third, air quality in Alaska poses an environmental justice issue, since my findings suggest that wildfire PM2.5 levels vary by subpopulation. Lastly, more research is necessary, as my study only sought out to start a conversation on a topic that received very little attention before, potential human health impacts of wildfire smoke exposure in Alaskan communities. I find this very interesting because the EPA does not consider air pollution from wildfires when assessing an area's air quality. And this is because the EPA does not consider, this is because the EPA considers wildfires as a natural source rather than an anthropogenic source. These are the studies that were mentioned throughout my presentation. And I'd like to give a big thank you to my advisor, my collaborators, and everyone in Alaska who have given me guidance and support, namely Eddie Hutzinger, Jim McCormick, Randy Chen, and Alice New York, as well as Allison, who I think is online here today. I'd be happy to take questions at this point.
This is Eric Miller with the Alaska Fire Service. Just a comment. This is very timely for resource management planning. I'm writing the fire management air quality section for the Bering Sea Western Interior, and this is some of the best information I've seen, and it directly relates to what I'm doing. So thank you.
No, thank you. Thank you for that feedback, and I'm happy that my research was of some value to you.
Hey, Lucia, this is Allison McConaughey. I'm at Mill and Boulder, and I look at these things more from a climate perspective, but this is really interesting, especially as far as the spatial distributions, that information that you've provided here. You know, we have sites on the North Slope of Alaska, and that looks to be like the hugest trend. When you look at those future predictions, they have lower exposures now and a lot higher exposures into the future. One question I have is this, the geochem product that you're using, does this have vertical distribution information for the wildfire smoke, and are you using that information just at the surface, or is this like just a grid cell average value?
Sorry, vertical information? Is that what you said?
Yeah, the emissions that get transported over Alaska. Do you have information about that transport vertically in the atmosphere, or are you just using some output from the model that gives you a surface concentration?
I believe that it's at the surface level, but for detailed questions regarding the models, I would be happy to put you in contact with my atmospheric scientists who were actually responsible for the modeling. And his name is Xiu Yue, and he can be reached at xu.yue@yale.edu.
Okay, great.
And this is Randy. I just have one comment. The future fire scenarios that Lucia used for this analysis were developed using models that were completely independent of kind of the scenarios that we're used to seeing developed from our homegrown al fresco modeling at UAF. These are some basically regression models of future fire that were developed at Harvard and Yale. The papers she cited that are using atmospheric components and weather components. Yeah, there's a citation. And but in general, they reach the same conclusions using entirely different methods. So I just thought that was interesting in terms of their future fire scenarios. They're not that much different than the ones we've been using in state.
This is Rangshai again. As far as the definition of wildfires go, most of these fires, I believe, are natural. What is the effect of human activities generated fires? Are they included in the model?
No, they are not integrated into the data set I've utilized. I believe that anthropogenic, so the way I derived the wildfire-specific PM 2.5 was that from the modeling, they produced two different data sets. One data set that included all wildfire emissions as well as anthropogenic emissions. And they developed another data set that had all of those emissions except for wildfire emissions. So what I did was I subtracted the second data set from the first data set to derive the wildfire-specific PM 2.5. So while my analysis does not deal directly with the human-caused emissions, I do believe that they are incorporated into the model.
Thank you.
Well, if there's no other questions, I want to give a big thanks to Lucia for taking the time to present this to our group. It's very interesting. It's from an ecological standpoint, we spend a lot of time thinking about the implications of future fire, but human health is an area that I really had never considered, and it's very important that we think of this as part of the picture.